So now we have our next group, which is Jason and Evelyn.
Hi, I'm Evelyn,
I'm Jason.
and our topic is ZX Algebra and Spider Fusion, and we're mentored by Dr. Gunty Cho. So we start by revisiting the block sphere. As Jesse and Angela mentioned earlier, every coordinate on the block sphere represents a cubit. We can also see from this diagram that each cubit can be represented by two angles, which are theta and phi. Next, we want to introduce ZX Calculus. ZX Calculus is the foundation of our research and is a powerful tool used in quantum computing to visualize and simplify quantum circuits. You start by rewriting like a quantum circuit as a ZX diagram, and then you simplify it using the properties of ZX Calculus. And then through these like efficient manipulation and optimization of circuits, we can reduce gate count, compilation time, and thus improve performance in quantum computers. And ZX Calculus is mainly built from two primary generators called spiders, the green and the red dot right that you see here. Spiders are scary in real life, but in quantum computing, they're your best friends. Okay, so these spiders are denoted by the green nodes, and basically they represent operations on the computational basis, which, as Jesse and Angela mentioned earlier, are the the 0 and the 1s. And then X spiders, denoted by the red nodes, represent operations on the Hadamard basis, which is just a transformed version of the computational basis that is used in quantum theory. And formally, a Z spider with n inputs and outputs and a phase alpha is represented by this mapping. So as I mentioned before, we can interpret like the block sphere, these spiders on the block sphere. So the Z spiders correspond to rotation about the Z-axis, which means the Z-axis is fixed and the rotations happen like this. And then in this graph, we can see that phi represents these rotations. And then X spiders similarly, like you fix the X-axis by its name, and they correspond to rotations about the X-axis, and in this angle, in this diagram, it'd be theta. And also another important part about a spider is their phase alpha, which corresponds to rotation angle. So it'd just be like the value of theta or phi. So as since ZX Calculus is like very known for its properties, we want to mention a few of them. And the first one is spider fusion, which means 2 points of the same type or the same color, like 2 Z spiders and 2 X spiders, can fuse together by summing their phases. Basically on the block sphere, it's summing the angles of rotation. And an identity is that a spider with no phase and one input and one output is the identity map. Basically, you put in a qubit and it doesn't rotate it by anything, so you get the same qubit out, which is the identity. And then the bialgebra law basically says that connecting a green spider and then connecting a red spider satisfies commutation relationships. So basically, a green spider and then a red spider is the same as doing a red spider and then a green spider. And then finally, Hadamard gates interchange green and red spiders. So it flips the axis of rotation and thus it's like the yellow block right there and changes the Z spider into X spider or the other way around. So looking at this example here, we have a quantum circuit, and the first step is to rewrite it as a diagram in ZX Calculus. So they turn the qubits into X spiders, and then the Hadamard gate into yellow block, and then they reclassified the separate gates inside the quantum computer as Z and X spiders based on the operations that they represent. And then the first step they took was we fused the two X spiders, the red ones on the top and also the red ones on the bottom, into one by applying the spider fusion law. And then we also flipped the red spider using the Hadamard gate into the green spider. And then using more spider fusion on the two Z spiders, and also noticing that the X spiders is the identity since it has 0 phase and 1 input and 1 output, we could combine those and make it the identity, which just finally results in just a Z spider at the very end with 3 outputs. But in reality, quantum computers are not that ideal. Like a block sphere cannot truly reflect the quantum computer, since in quantum computing there is something called noise, which acts like a singularity, and since that is not isomorphic to the other points in the block sphere, we wanted to find the weighted projected line. So as Jesse and Angela mentioned earlier, this is the formula for the weighted projected line. And instead of a scalar multiplication, the scalar multiplication is instead weighted by like exponents A and B. And due to this equivalence relation, there are now singularities for the North Pole and the South Pole, like how the block sphere like extended. And this just means that or the definition of singularities at points on this orbifold where the local neighborhood cannot map to a circle on the Euclidean plane. And we can see by this diagram here that on the Bloch sphere, the rotation at the top is a full 2 pi. However, when we take the weighted version of it, where it's CP1, where it's like 1 and 3, at the top it's only a 120-degree rotation, and that this is because at the top there are multiple stabilizers that make it the same. And yeah. So with the weighted projective line, we also want to establish a new weighted ZX calculus. So a weighted z-spiral is denoted as the following, and the two new things that we introduce are the weight, which is the phase equivalence modulo 2 pi over a, like on the previous slide, the diagram. After 2 pi over 3 degrees of rotation, it restarts. So that is why the phases are equivalent. And then we also introduced the Winding number k, which is counting how many times the phase has wrapped around 2 pi, so we can keep track of how many full revolutions have happened. And because of this definition, our new total phase is represented as theta equals alpha plus 2 pi k. And with our new framework for a weighted ZX calculus, we also want to establish a few objectives. We first want to show how our weighted ZX calculus differs from the normal one, and how does it better model the true properties of quantum computing hardware. We also want to represent the previous properties of ZX calculus, such as the spider fusion law and the identity that made it so useful in this new weighted version. And we also want to show, like, realistically how this improves error correction, circuit simplification, and other concerns that we use in quantum computing. And we also want to run experiments to show these improvements. So, like, we have a real, evidence that it's better.
So to reiterate on the previous definition of winding number in the previous slide, a winding number is given a path that rotates through, that goes through an angle. If we divide that total angle by 2 pi, and given this our phase is cyclic, this will tell us the number of full rotations made by this path. So reiterating over the previous definition for the weighted z-spider, the weighted z-spider has a phase A, which tells us the angle through which it will rotate on the Bloch sphere. And the winding number k keeps track of how many full rotations have been made by these spiders. And then we have a weight A, which encodes the discrete phase identification, which is basically how we mod our phases, such as compared to before in the full normal sphere, a full rotation is mod 2 pi, but with the new weight, it's now like mod 2 pi divided by our weight A. So here we have two figures. In figure A, it shows how rotations around the orbifold, where the top path represents rotation around a singularity at the top point, the point and cone point, while the bottom path represents a general path around points not at singularity. So despite singularities themselves having a quicker orbit, so long as both paths make a full rotation around the sphere, they both represent a full 360, they both represent one winding. And then in figure B, it just generally shows how a winding is not restricted to just strictly circular paths, but just any path that eventually returns back to its original state. So now that we've defined weighted spiders, we now propose a new weighted fusion law for these spiders. So if we're given two spiders of the same type, we can fuse them together into a new spider whose weight is the least common multiple of the two spiders it was fused from, and then we can combine their phases proportionally such that they maintain the same proportions, and then we can sum up their winding numbers, as winding is unrelated to weight, and it just simply represents a full 360 rotation for our spiders. And then in our working document currently, we use von Neumann algebra to prove that our new law will follow the standard law, where it's associative and commutative, and we can still extract the phase equivalence by using our weights and our winding numbers. So moving forward from here, we hope to simulate and compress circuits to test the effectiveness of this new fusion law. So to begin with, we're going to convert traditional or normal quantum circuits into a ZX diagram, where we can then encode the gates as weighted spiders, where we can then apply our fusion law, our weighted fusion law extensively until we can no longer apply it. And then in doing so, we will recalculate the phases for our spiders and continue to keep track of the winding numbers. And in doing so, at the end, when we finally fuse everything, we will remove any redundancies, any full rotations, so that we can get rid of any extra spiders or any extra rotations. And then afterwards, we will extract this new compressed circuit back into a quantum circuit such that we can test it and record the final gate count, the circuit depth, and the number of spiders that were used in our circuit. So generally, we will be keeping track of in the end, we will evaluate our results based on the percent decrease in gate count and circuit depth. In this context, gate count is essentially the number of gates that will have to be used for the circuit to compute, and circuit depth will be essentially the parallel runtime of this new circuit. And then we will also be keeping track of compression time, or the time needed to compute this new compressed circuit. This is all very significant as this new idea of a weighted spiders and their weighted fusion law will take into account the noise that's inside quantum hardware in the real world. But also, it's also more generalized, as when you set the weights from before, the A and B, back and set them to 1, it'll encapsulate the previous model entirely, and it still represents the current state fully. And then it also helps. This new method will also help out with error correction and circuit optimization, as now, thanks to the weight, we can keep track of any potential noise that is affecting our circuit, and we can also keep track of any redundancies with the winding number, seeing how there could be extra full rotations that we do not need.
As Jason mentioned before, we want to run simulations to show improvements on our realistic model. And so as we already mentioned the circuit simplification simulation, but we also want to add in a few other simulations regarding phase accumulation, which is what he said about the significance, and also distinguishing of errors, since now we have the winding number and we can distinguish between two different things. And then we also we want to compare our standard decoder and our monodromy aware one, which just takes into account the singularities, and we want to compare the surface decoder, which is another big part of quantum computing. And finally, we want to investigate the time and memory costs associated with using spiders, since now we're including two new variables, which are the winding number and the weight, so that will just take more memory. And also, when we do our spider fusion, the calculation and computation is a bit more complex than previously just summing the two spider phases. So we also want to investigate the time that it takes to simplify the circuit. We would like to thank Dr. John Hee Cho for his guidance and support, MathWorks for their encouragement, the faculty for their teachings and dedications that gave us the background for this research, our coordinator Jerry John for his feedback, and the audience for their kind attention.